Welcome to Lesson 7a, Critical Area Ratio Across a Normal Shock. In this lesson, we'll derive an equation for the critical area ratio across a normal shock, and then I'll show how to apply this equation in a converging-diverging nozzle. Let's start with our standard converging-diverging nozzle, where a shock is located here. We know that the flow is subsonic upstream of the throat, sonic at the throat, supersonic before the shock in the diverging portion of the duct, and then subsonic again after the shock, where of course we generate this condition by adjusting the back pressure appropriately. We know that the flow is isentropic all the way to the shock in the converging and diverging regions, so the area ratio equation, A over A star, as a function of Mach number and gamma, applies. The flow is not isentropic across the shock, but downstream of the shock, the flow can be approximated as isentropic. So again, our A over A star equation applies. But the problem is that A star changes across the shock. So for known throat area A star, we'll have to call this A star 1. This A star is valid through the entire flow up to the shock. But downstream of the shock, we have some A star 2, which applies downstream of the shock all the way to the exit plane. These equations are valid, except we must put a subscript 1 upstream of the shock and a subscript 2 downstream of the shock. As a quick review of a previous lesson, you may recall that A star 2 is greater than A star 1, as I've sketched here. This area is greater than this area. And what I've sketched here is an imaginary second throat. In other words, it doesn't really exist in this flow. This portion of the flow is a diverging duct. But if we did have these walls, we could accelerate this subsonic flow to sonic here. That's how we define A star 2. And as I said, A star 2 is greater than A star 1. But let me ask the students, how do we calculate A star 2? In particular, what equations do we need to solve for A star 2?
Could we use conservation of energy?
Correct, Mr. Kelvin. Now I need another equation.
Could we use the Fano or Rayleigh equation?
That would just give us P2 over P1, Mr. Palpatine, but it wouldn't help us get A star 2.
What about conservation of mass?
That's what I'm looking for, Freddie. Let's use conservation of energy and conservation of mass. I'll apply these two conservation equations to generate this ratio for an ideal gas. Recall that in our converging-diverging duct, I usually don't sketch the insulation, but we're assuming that the walls are perfectly insulated, so there's no heat transfer. And even though there's a non-isentropic shock, T02 equal T01 by the conservation of energy equation. That's because H02 is H01, and we're approximating an ideal gas. Now apply conservation of mass. Let's apply it at the real throat, where we call A star 1. So m dot 1 is rho star 1, v star 1, A star 1 at the real throat. And as we've discussed, we have an imaginary throat of area A star 2 downstream of the shock. So m dot 2 is rho star 2 v star 2 A star 2 at the imaginary throat downstream of the shock. But conservation of mass tells us that m dot 1 must equal m dot 2. The same amount of mass flows through the nozzle regardless of whether there's a shock or not, because there's no leaks through the wall. There's no other place for the mass to go. Before I continue, I want to comment that we can use A star 2 in our analyses, even if it does not actually exist anywhere in the flow. We've stated similar things for A star itself, for little a star, T star, etc., which we've used even in cases when they didn't exist in the flow. In this case, A star 2 does not exist, but we can still use it in our analysis. Now let's set these two equal to each other because of this equation, and I'll use the choked or maximum m dot equation that we had from a previous lesson, namely P01 A star 1 square root of gamma over r t naught 1 times gamma plus 1 over 2 to the negative gamma plus 1 over 2 gamma minus 1 must be the same thing at 2, but with all these subscripts changed to 2 instead of 1. But from our energy equation here, T naught 1 and T naught 2 cancel out, and all these terms with gamma and r are identical on both sides, so all of this also cancels out. So we're left with a very simple equation, namely a star 2 over a star 1 is P naught 1 over P naught 2. This is the critical area ratio across a normal shock. Well, from a previous lesson, we already have an equation for this. In particular, we had an expression for P naught 2 over P naught 1 in terms of M1, M2, and gamma, or in terms of just M1 and gamma. And since a star 2 over a star 1 is the reciprocal of this, we can immediately write this equation for a star 2 over a star 1, either in terms of M1, M2, and gamma, or just M1 and gamma. We usually know M2 across the shock, so this one's a little bit easier to implement. Now let's verify this equation with our standard case. Namely, as we've done in previous lessons, we'll let M1 equal 2.60 and gamma be 1.40. The above equation gives a star 2 over a star 1 equal 2.17333. Now let's compare this to the results calculated by the compressible aerodynamics calculator online. We go to the normal shock relations. Gamma is already 1.4. We change Mach number 1 to 2.60 and calculate, and unfortunately we don't see an A star ratio. However, we see the stagnation pressure ratio, 0.460123, and we know that A star 2 over A star 1 is 1 over the ratio P naught 2 over P naught 1. Here, 1 over 0.460123, which gives us 2.17333. This agrees with what we calculated with our equation, as it must since this is such a simple equation. Now I'll show you qualitatively how to apply this area ratio in our CD nozzle. We know how to go up to the shock, where we calculate M1. We know how to calculate M2 across the shock. We know that this area is A star 1, and this imaginary area is A star 2. So in application, we use area ratio A over A star 1 here upstream of the shock, but we use A over A star 2 as a function of Mach number and gamma downstream of the shock. I'll make two quick comments. Namely, A star 2 over A star 1 was 2.1733 at our test case. So indeed, as we've been saying and sketching, A star 2 is greater than A star 1. This is because P naught 2 is less than P naught 1 because of the sudden jump in entropy across the shock, as we've discussed previously. And comment 2, I will do an example of calculations in a CD nozzle with a shock in the next lesson. Oh, and I'll add a third comment. Make sure you use the subsonic route in this equation downstream of the shock, since the flow there is subsonic, not supersonic.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.